Okay, welcome to our video today. In this tutorial, we're going to look at electromagnetic induction. We shall get a coil, connect it to the galvanometer, where you see the word voltage, and for the purposes of clear observations, we shall include the bulb there. And we have the magnet. So I'll position the magnet there. And if the magnet is kept stationary like the way it is, what do we observe? We do not see any deflection on the galvanometer, and also the bulb does not light. When this magnet is moved into the coil, we see the galvanometer deflecting momentarily on one side and also the bulb lighting. When we pull this out, still the galvanometer deflects, but now in the opposite direction, and the bulb again lights. What is causing the bulb to light and the galvanometer deflect is simply the current that flows through them. But current can only flow if there is an electromotive force driving it. And I'll ask now, in our circuit, do we have the source of electromotive force? The answer is no. So what is simply causing the current flow through the bulb and the galvanometer is simply the induced e.m.f. that is set up in the coil due to the movement of the magnet. Let us try to explain this more. If we put in the fields onto the magnet, you discover that the magnetic field lines of the magnet, or what we call magnetic flux, links up with the coil. When the magnet is stationary, the magnetic flux linkage is not changed. When we try to move the magnet, what we simply do is we change the magnetic flux linkage, and as a result, an e.m.f. is set up in the coil. This phenomenon is what we call electromagnetic induction. Let us also look at this. When you look at the direction of our field is to my right, and when the magnet moves into the coil, the current flows in the opposite direction, and you see the galvanometer deflecting in the opposite direction to that of the field. Okay, when you pull it out, it's the same story. We can change this magnet also. So now the field is pointing to my left. When I move the magnet into the coil, the galvanometer deflects to my right in the opposite direction. Also look at this. If we move this slowly, if we change the magnetic flux slowly, what do you observe? If we move it slowly, the deflection is small and also the lighting is dim. When we try to move faster, that is, we are changing the magnetic flux linkage faster, then the deflection is much and also the lighting is brighter. Okay, so this was discovered by Michael Faraday, and he came up with the laws of electromagnetic induction, one named after him, and that is called Faraday's law. Faraday's law will state that the magnitude of the induced e.m.f. is directly proportional to the rate of change of magnetic flux linking the coil. We also have the second law, which is called Lenz's law. It states that the induced EMF or current acts in such a way so as to oppose the change causing it. That is what we call Lenz's law, and those are the two laws of electromagnetic induction. In summary, if we talk about electromagnetic induction, this is what we can say. Thank you for watching. Subscribe to our channel for more videos, and also share the video with a friend so that we all learn. Thanks.